Any questions? So you see the material for the midterm, for the final, that is, right here. Materials for the final, which is the tailing end, probably the tailing end of dynamic programming and everything right after it. I mean, wait for the final message. Maybe I'll have fresh and dynamic time warping included, maybe not. I'll still think about it. Definitely this is. Might include a bit more or a bit less. But essentially that's it. The format of the final is essentially the same format as the midterm or any other exams that you took with me. Same policy, probably I'll have to look about copying if I want to have you only written using handwritten or do the same thing. So it might be that I'll try to make it a bit harder to cheat. Maybe. Not that anybody of you ever did, but to make to give the good feeling for everybody that I did everything to prevent others from cheating. I think that is important. Okay, any questions? Okay, so let us continue with talking a bit about homework 4. The homework 5, sorry. The homework 6 people are still playing with, so I'll not talk about it yet unless there are any questions. And I'll yes, of course. You can submit late. Sure, you can submit late. But don't forget that there is homework 7, so manage your time. Okay. From homework 5, maybe the easiest question was question 7 that talks about the edge cover. That is, I'm given a graph AG, and I want to find a set of edges such that the set contains as few edges as possible, and every vertex is covered by at least one of the edges in the set, which was just the analogous of the vertex cover that we played with quite a bit. So how should we do it? Phrasing as an linear programming at the moment, and it will become integer linear programming in a second. So I want to, my variables are x1 ... xm. M is, as usual, the number of edges. And for every vertex u in V, I want this sum to be at least 1. Let's understand what's going on here. I picked one of the vertices u, and I'm looking at all the neighbors of u, all the edges that have an endpoint at u. The idea is that we want to pick in the cover, pick to the cover either u A or u B or u C. These three edges, u A, u B, u C. At least one of them must be in the cover. We don't mind that, all three. So xi is a variable where xi equal 1 as usual, xi equal 1 if and only if edge I is in the cover, edge EI. Unreadable. Edge EI is in the cover. So I'll have my three Boolean variables for the one per every edge that leaves U, and I want that one of them will be in the cover, so one of them must be at least must be its characteristic variable that says should I take it, should I not take it to the cover. One of these three edges must be picked, so x of UA, the Boolean cover that says should I use the edge UA, plus XUB plus XUC should be large or equal than 1. Right? Makes sense, correct? One, that will mean that at least one of these three edges should be covered. And our cost function would be, of course, we want to minimizing the number of edges that we are using. So in the unweighted case, I want to minimize sigma of xi. These are my variables. As usual, xi is between 0 and 1. And every xi should be an integer. And of course, and the solution to this problem would be the would be the optimum edge cover. Maybe that was the easiest question in the homework. The question that I asked the graders to grade most harshly was question 9, because people that made some of the typical mistakes that I'll mention in a second, some of the people that made the typical mistake just kind of demonstrate they didn't play with the first question, didn't play with a diet problem, thought that it's a bit more serious of, without knowing to answer question 9, the whole deal of linear programming makes absolutely no sense. So let's see what were some typical mistakes. So out of all these points, for some of these points, I can find values of Ci and Di such that Ci xi plus C Di yi for one of the points is the extreme point, give me the best value out of all the other points. That is, that this value will be strictly smaller than, say, Cixj plus Diyj, when I is different than j. And the question was, which of these points can you find such values and which of the points you cannot? And the way to think about this question, we think about if I just fix C and D, if I just fix C and D and ask where are all the points such that Cx plus dy equals 17, where are all the points that this is satisfied, and no matter what are the values of C and D that I picked, this will be some line that depends on picking C and D. And if I'll ask where are the points where C, this value, where are the x and y for which this value equals to 18, it will just be a line parallel to the first line. That is where it's 17, 18, 16, and once I picked what is C and D, I picked the orientation of this line, and now I kind of sweep the plane with this line, and I'm asking where is the first point that I hit, because the first point, P4 in this case, is where this value is minimized. The value of the cost function is minimized. That's where I have my cheapest diet that is still healthy. C and D might be the prices of oranges and bananas. So I'm just asking which points can I generate that will be actually the optimum or the extreme point in the direction which is orthogonal to this line. And you look at this set of points in the homework, you have a fewer points, and you realize that P3 somehow is will not be the minimum of any cost function. This problem right here in the middle, and let's stay still with definition of what is middle, kind of vague, but somewhere being in the middle means that if I'll come up with a line from this direction, I will hit P4 first. If I'll come up from the top down, I'll hit P1 or P2 first, etc. No matter which one I will try to get, P3 will not be the first one that I'll do when I'm moving with one of these parallel lines. And if you look at it a bit more clearly, you see that there is this notion of convex hull. Namely, which is just the intersection of all the half planes that contains all these points, or just defined by all the extreme points, all the lines that have all the points that have any chance to be the minimum of my cost function if the cost of oranges and bananas are correspondingly right. And it can be positive, can be negative. But a point like the one in the drawing of the homework, which is inside a triangle, in the middle of a triangle, defined by 3 other points, will never be the extreme. So people that got it right, great. People that said that we only care for the leftmost or the rightmost and the bottommost and the topmost, I had the feeling they didn't play with other parts of the linear programming, so that was a bit. So I didn't ask you to generate an algorithm to find all these points, but you can still, for each one of the points which are on the convex hull, you can find a tangent line, which is essentially what you want. The tangent line per a point, will I be able to do it? This tangent line that just touches this point but have all the other points from one of each side is exactly determined by the C and D, for which this point is a minimum or the maximum out of all the other points. Questions about it? Okay. Other questions from this homework that you want me to discuss?
So just to clarify, you said if we said that the weights that were the topmost, bottommost, rightmost, leftmost, you said that was incorrect?
If you said that there is no way to generate other points, I need to see what exactly you said. If your answer works only for this example but doesn't work for the example on the whiteboard, then it's not the correct example. But I need to see what you said so I'll know how to panelize it.
Okay, thank you.
The question that I thought that is the hardest is the question that I thought that was the hardest was a question that asked about LP versus ILP. Question 6 is you were asked, is there any similarity between the values that we are getting in the LP and the values that we are getting in the ILP? Then we say that the linear programming is somehow a good approximation to the integer linear programming. And the answer is that sometimes yes, sometimes no. But essentially, if even in 2 dimensions, here is my integer grids, 1, 2, 3, 4, 1, 2, 3, 4. Here are the points which are integers. But this will be the point 1, 0. This will be 1, 1, and so on. Here are my integers, and the question was to find constraints such that the optimum of the linear programming will be somewhere here, very close to the origin, while the only solution to the ILP will be, say, the point 3, 4. Only this integer. That is, that there is a big gap between this point and this point, say, as far as the height. If you can do it with 3 and 4, you can do it with 100 and 200, and the trick was to first generate a line, pick this integer point, and now generate a line. You can always rotate this line and make sure this line passes through one of the integers only once in a while. There are only 3 times 4 or 100 times 100 many integers, so for most angles you don't hit any integer, which means that if I'll place my other point along this line, and of course Murphy law, I need to, and let's move this integer over here, so I missed all the integers through this line, then if I look at the lowest point of this segment, it will be this one. If I look at the lowest integer point along this line, it will be this one, quite far, far away, and there is no other integers in between. And then you just need to express this line as the intersection of a few half planes. A bit tricky. Okay. Question 5. I hope that everybody got the factor 3 approximation. It was, by the way, our brief visits into approximation algorithms. We talked about factor 2 approximation or factor 3 approximation. That is, algorithms that look at an NP-hard problem, doesn't necessarily find optimal solution, but find something that is not more than 3 times the optimum. And in the unweighted case, to find factor 3 approximation is what I mentioned as Bar-Yehuda algorithm, which says pick an edge, take all its 3 vertices to be in the cover. You want to cover all the edges. Each edge, however, is what we call hyperedge. It goes through 3 points, not only 2 as in a graph. So I'll pick one of the edges. One of its 3 points must be in the cover. Instead, I'll take all 3 points to be in the cover, and I'll remove from my input all the edges that I just hit, that I just stabbed. And pick another edge, take all its 3 points, etc. Now, since for every point in the optimum I used 3 points, I know that my solution is not more than 3 times, and you don't see it at all. I'm sorry. Since my point, this question I know that if I'm looking at C1, one of its 3 points must be in the cover. Instead, I take all 3 points to be in the cover. On every $1 that I could have used for the optimum, I'm using $3 for my stupid algorithm. And once I used these 3 vertices, then of course I don't need to worry about any of the edges that are stabbed by any of these 3 vertices. So I'll just move to C2 because it's the only one that is not stabbed by one of these 3. And that's obviously factor 3 approximation. And when you are looking at the weighted problem, of question 5, then this greedy approach can take you far, far away from the optimum. Instead, you are solving it using LP, linear programming, not ILP, but LP. And now every value xi which is larger or equal than third, you're taking this I and you push it up to be 1. That is, everything that is at least third, you're pushing to be 1. And if xi is smaller than third, you're pushing it to be 0. And then you need to essentially write all the variable to say why this is factor 3 approximation. That was a bit lengthier. Any questions? Goody. Let's talk about Ford-Fulkerson algorithm for 0-1 networks. So I always have a dilemma about the network flow and the big mean cut max flow theorem. It's a very important theorem. It's in the syllabus. Ford and Fulkerson and Edmund Karp algorithm are in the syllabus. I have problem teaching it. Students don't like it very much, and I don't blame them. So I'm doing now, I'm trying it the first time. I think that almost all the components of the big network flow problem for arbitrary capacities, or at least a lot of these of the component of both the algorithm and the structural theorem behind it, they all preserve in 0-1 network where the capacity of every edge is 0. The capacity of every edge is 1. A lot of the main tools that we are developing for the big network is preserved for 0-1 network, but they are much more friendlier, and notation are exponentially simpler when we are using 0-1 network. So once again, my graph is not necessarily bipartite. I still want to find a maximum flow problem, which defines by graph which is directed, one vertex S, one vertex T. The capacity of every edge is 1. I want to assign value for every edge of the flow such that the total flow that leaves S will be as large as possible. And at the very same time, for every vertex that is neither S nor T, whatever comes in must be equal to whatever goes out. The flow going into a vertex, which is not S or T, must be equal to the flow that leave S. or t. And the algorithm itself will give a solution that is optimal but also integer, which linear programming, for example, does not always enjoy. Linear programming for this problem might result in a solution that consists of floats. This will not happen just because of the way that Ford-Fulkerson algorithm works. So let's play with this example. I'll assume that the flow of every edge will be either 0 or 1, between 0 and 1, and I need to define the residual network. And my definition of residual network is similar but somehow simplified than the definition that you'll find in the textbook. Definition in the textbook is works for any capacities of the edges. My definition will work for edges for the capacities that are only 0 or 1. Capacity that is only 1. Edges with capacity 0 are not very interesting. So, what is this residual network? I'm looking at the flow at the network at the moment. I'll start when the flow is 0, but it's going to change as the graph progresses, as the algorithm progresses. And I'll define a new network, this residual network. How is this defined? It's an output of both the original graph, G without the F over here, and an output of the current flow. To be precise, I'm looking at an edge E of E, edge of the original graph, and if this edge carries no flow, then I take this edge and insert it as is into the residual network. EF will contain the original edge UV. Edge that doesn't carry flow is not changed at all. If an edge carry flow, then I'm not inserting it into the residual network. Instead, I'm inserting an edge that is just directed in the opposite direction. Not the edge UV, but the edge VU. That is, I flip the direction of the edge. And now I know what is EF. And my next step in Ford-Fulkerson algorithm is to find any path pi from S to T. Find any path whatsoever from S to T. And once you are finding such a path, augment it. Let's see in the example, what do I do in augmenting it? So I start when the flow is 0 on every edge. That's obviously legit because it satisfies both the conservation constraints and the capacity constraints. 0 is less than 1. And what into V1 there is a flow of total 0. There is a flow of total 0 leaving V1, so V1 is happy. Find what is GF if the flow is 0. Let's follow the rules. If FUV is 0, then insert UV into the residual network. The edge from S to V1 carries no flow at the moment, so it is inserted, just as is into GF, into the residual network. The edge from V1 to V2, inserted as is. And so on for each edge. I don't reverse its order yet. I'll insert it as is into GF. And now I'll find a path in this directed network. Find a path in GF. Let's find such a path, and since I wanted to be a slightly interesting example, here is the path pi that I find. From S to V1 to V2 to T, and once I find the path, I can augment it. How do I augment it? For every edge UV on this path, every edge that is also exists in the original network, which means it carries no flow and it was not reversed, meaning that I can increase the flow along this edge, I can increase the flow across this one, and I can increase the flow across this one. So that's exactly what I'm doing. increasing the flow by 1 across every edge in this direction. And at the moment, we still don't see this very bizarre, very strange condition of canceling flow. It will come next. So what is the flow at this moment? Let's look at the resulting graph plus the flow. There is a flow of 1 goes from S to V1, go from V1 to V2, go to into T. Very happy. And now the algorithm tells us repeat, oops, I deleted it. Repeat this whole process as long as you don't need to exit. Exit here will happen only because you cannot find any augmenting path. This is so let's generate the residual network with respect to this network, to G, and with respect to this flow. There is a flow of 1 across one of the edges. So the edge from S to V1, it carries a flow, so I need to reverse it. It will be inserted into GF, but in the opposite direction. The flow from S to V2 does not carry flow, I don't reverse it. The edge from V1 to V2 carries a flow, so you need to reverse it. Don't reverse, do reverse, because there is a flow going from V2 into T. And now you find a new path in this graph. So I'm trying to find such a path from S to T. I cannot go from S to V1 because the edge is directed in the opposite direction. It's not an edge that leaves S, but I can go, however, into V2. Let's go to V2. From V2, I can go to V1, and from V1, I can go to T. And once again, I'll perform this augmentation. For every edge across the path, every edge UV across the path, the edge S to V2 originally did not carry a flow, so I can add a flow of 1 into it. The interesting trick happens along the edge V2, V1, this vertical edge. Remember, the original edge is going downward. The new edge in GF is going upward, so I can push flow of 1 upward, which essentially will cancel the flow that is going downward. I'm canceling the flow going downward by flow going upward, which eventually will imply that I just cancel the flow across this edge. It's plus minus 1, giving me 0 across this edge, and I can give a flow of 1 across the edge V1 to T. So my new graph will be this one. Flow 1, flow 1, flow 1, flow 1. And at this point, when I'll generate GF right now, what happened to GF at this moment? Remember, every edge that carries a flow is reversed. So the edge from S to V1 reversed. The edge from S to V2 reversed. And that's essentially the only interesting case in this part, because the moment that there is no edge going from S, it's a done game. At this point, I cannot find any path from S to T, and then the algorithm stops and tells you this is a maximum flow. You find a flow that no other algorithm can do any better. That's a global maximum flow. Okay, so a bit confusing. Why are we doing this reversal of an edge? And remember what we discussed last class. Why do I do the reversal of an edge from S to V1 to V2 into T? What I'm saying is that if I'll add plus 1 to the flow going across this edge, and I add plus 1 across the edge going into V1 and the edge going out from V1, then V1, if it kept the flow conservation before, what comes in goes out. beforehand, then now flows at 1 plus 1 altogether will cancel each other. However, if there is already a flow that is going in the opposite direction, this is the original flow, I can still do this trick by just canceling the flow going upward, which will mean that there is a flow of a plus 1 going in, but there is stopped being a flow of 1 coming across this edge, so V1 will have no reason to complain. It's still flow conservation. And on top of it, the edge from S will never be, when I'm adding to 1 to the edge that leaves S, I'm increasing the total flow. When I'm adding 1 to the edge that leaves S to V2, I'm increasing the total flow. So any augmentation will add 1 to the flow across each one of the edges that leaves S, which is where I'm measuring the flow. By the way, if the capacities was not uniformly 1, but could have been different value for every edge, I will still do the same augmentation. I will still do the augmentation across the path, adding some value to every edge across the path, but now this value is not necessarily 1. It will be something that depends on what are the capacities of all the edges, how much flow do they carry, and I'm just carefully increasing the flow across this path by the same amount. Instead of 1, it will be some delta, but still the same delta for the whole path. And I'm just picking delta such that none of the edges across this path will exceed its capacity. This capacity might be larger than 1 or might be non-integer, but I'll never exceed the capacity of some of the edges. So I'll just look at the bottleneck across the path, and this will tell me by how much to add. Okay, another example. Here is a maximum matching problem. Once again, here this was my bipartite graph. A, these two vertices, B, these two, and I added S and T. I'm sending a flow of 1 across the upper link, so there is a flow of 1 over here. It is not the maximum flow, yet I cannot add the flow greedily to any of the edges over here, because if I'll send a flow of anything to A, then this flow needs to leave A into this node, when then the flow of 1 coming in from this edge plus whatever I'll send through the diagonal edge needs to leave through an edge that is already saturated, implying that I need to find a hint to cancel the flow across the horizontal edge. And once we are generating GF, the residual network, the edges that carries a flow are reversed. That is, they go from this vertex to S, from this vertex to the left. Remember, that was the original edge. Now it reverses its direction from T backward. And the path that you'll find now as an augmenting path, do I have this animation? Yes. This will be the path that you're going to find. And when you augment the flow by 1 across any of the edges, what will happen? This edge, the diagonal, will be in the matching, carry a flow of 1. This edge in the matching, carry a flow of 1. This edge, horizontal edge that carries a flow of 1, this flow will cancel. It will carry a flow of only 0. We are sending 1 to this direction and canceling it by sending a flow of 1 in the opposite direction. Another schematic way to look at Ford-Fulkerson, another schematic way to look at Ford-Fulkerson will be start where the flow of every edge is uniformly 0, and while 1, this is not how you end the loop, as long as you can find, you are at every iteration, build the residual network, try to look for an augmenting path in GF. Don't forget also what was the definition of augmenting path that we had in the case of a bipartite matching. It was very similar. find an augmenting path in GF for the network flow. If you find a path, be happy and augment the total flow across this path. If you cannot find any such path, time to stop, you find the maximum path, the maximum flow. Any questions so far? Everybody perfectly understands the algorithm? Super. Moving along, and to start understanding the structure of the flow and why Ford-Fulkerson is indeed will end up only if you find an optimal flow, we need to use, we want to write down the max flow mean cut theorem, and for this we need to define cuts. Here is a definition of a cut. A cut is of the network. It's a poor choice of letters, but all the textbooks that I saw use the same notation, so I'm going with the string, and I'll use the same letters. Capital S, at least I'm adding boldface, and capital T. So a cut defined by one set capital S and one set capital T is a cut in the network if the following happens. I take all the vertices of V, I put some of them in S. In this example, I take small s and A and put both of them in capital S. I took every other vertex not in capital S, and automatically every vertex not in capital S is in capital T. Again, it's a partition. If you're not in capital S, then you must be in capital T. Every vertex is either here or here. Small s, the source, must be in the capital S, and small t, the sink, must be in capital T. Otherwise, it's not a cut. Okay, and there are exponentially many cuts that you can define for the same network. We will not bother enumerating all of them. We don't need all of them. We will definitely use this definition. So remember, a cut is any partition of all the vertices into two subsets, such that S plus maybe some other vertices are in the left subset, and T plus maybe some other vertices are in the other subset. And now let's define the flow across the cut. First, here is a formal definition with a lot of letters. The intuition is not complicated at all. Intuition is not complicated at all. I want to ask how much of this flow, if I just take my network and chop it in the middle. Let's demonstrate it by, if I'll take my network I will take my network, here is S, here is T, and I want to now cut the network somehow. Now remember, S is keep pushing water into the whole network, but now this water is falling from the end of the network. So I'm just asking how much water are falling now outside from this cut. That's the whole intuition. So the formal definition is saying I'll look at all the edges that are going from S to T. Look at all the edges of the network that are going from S to T. It's like try to imagine standing with two legs. One leg is in S. Here is my whole network V. Here is small s. Here is small t. Here is pictorially the cut. And now there are some edges that pushes flow from a vertex U, which is inside capital S, the left set, into a vertex V, which is in the right side. This is in capital T. So I look at this edge, I look at this edge, I look at this edge. They are all pushing flow from left to right. But to confuse me a bit, this is not necessarily all the flow that S sends, because T by itself, we'll see an example in a second, T might send also flow across some edges from a vertex X that is in T into a vertex Y that is in S, like a flow that is going in the opposite direction. So again, I'm going to cut the network. I'm going to look at flow that is sent from a vertex of capital S into a vertex of capital T, like this one and this one and this one. But unfortunately, I also have to account flow that is going from some edge A that belongs to T into some vertex B, that belongs to capital S, and I'll have to pay some attention to these edges. So now let's get back to these many symbols, arguably the most indices that we had in this course. Yeah. I mean, thanks, but I cannot read when I'm with my head into the whiteboard. Thanks. But yeah, you got the intuition of what is this cut. You can also see the cut over here. Let's see the definition. Look at all the flow across edges that goes from one vertex of S to another vertex of T. These are the green edges. There is a green edge that going from S to B. There is a green edge that goes from S to C. Who else is in my cut? And as I said, the cut is completely arbitrary. You can define lots and lots of different cuts, and each one of them is legit. You cannot go wrong with a cut. The only thing that you can go wrong with is either that T is not on the other subset, or S is not in the first subset, or that you counted the vertex both in S and T. Other than that, every partition is legit. I decided that my cut defined by S and A, so automatically the remaining vertices belongs to capital T, and now I'm counting the flow that crosses from a vertex in the cut to a vertex outside the cut. I sum up this one plus this one plus this one. They are all vertices. They are all edges going from being in the cut to being outside the cut. Edges that cross the cut. So, and this is a fourth edge. So I need to sum up the flow. In this case is 1, by the way. The flow across the edge SB plus SC plus AC plus A1. I used green to say that they are the good flow, and out of it I am subtracting the flow that is going from an edge which is outside of the cut into from a vertex outside of the cut into a vertex in the cut. That is a vertex. This is this term of the summation. I'm summing up for FUV when U now is in T, in the right side, and V is in capital S. And these are the coming with minus sign. These are the red ones. So there is a flow of 1 going across this edge. There is a flow of 1 going across this edge. Notice this edge B is in T, A is in capital S. So that's why it's in red. The edge SC is from a vertex in S to a vertex in T. That's why it's in green. And you just sum up all these numbers. So in this example, it will be 1, 1, 1, 1 across the green minus the 2 ones across the red. Notice there is a flow of 1 from C to E, but since C and E are both outside in the same side of the cut, both of them are in T, we don't sum it up. Also, if I had a direct edge from S to A, I would not sum it up either. Only edges that are bichromatic are summed. Nobody understands why this definition is good for and why I cannot only look at natural cuts and I need to define so many strange cuts, but I hope that at least people understand what the definition itself. Not why it's good for, but at least what is the definition, this summation of flows. Here is our first important lemma. We defined the value of the flow, I didn't write it, the value of the flow as the total flow that leaves small s. I looked at small s and I asked how much of this flow is leaving small s, and summed it up over all the edges that leaves small s, the source. The source, think about it as usual as the source is Netflix, T is one of the customers. We want to stream a large file and we want to do it by using the capacities of the whole internet. So we're asking how many bits per second leaves Netflix per every second. And the lemma tells us that if you look at any cuts, as long as it's legit, the flow across the cut is exactly the value of the cut. In other words, going back a slide, I could have checked the flow that leaves S itself. By definition, this is the value of the flow. The flow that leaves S, small s only, consists of the flow from S to B, which is 1, plus the flow from S to C, which is 1, so the value of the flow here is 2. What does the lemma tells me? If instead of checking it only in S, but check it across any cut, you'll get the same value. It is. In this example, the flow across the cut, F, note the notation, it's a bit confusing. It's the flow when I write capital S and capital T. That's a flow across the cut, this summation that you see over here. The lemma tells you no matter where you'll pick your cut to be, which vertices are in the cut, small s must be there, but which other vertices are there, as long as T is not there, compute this summation, you'll always get the same value, which is just the flow that leaves S. Proof by example, 1 plus 1 plus 1 plus 1 is 4, minus 1 minus 1 that goes into the cut. 4 minus 2 is 2, which is indeed the flow that leaves S itself. In particular, another cut that I can pick will be the following, by the way. I'll say that capital S will be all the vertices minus the vertex T. And capital T would be just the vertex small t over here, the sink. Not really surprising, but still needs a proof. If I look at the flow that leaves S, and remember, nobody here conserve any flow. The water that arrives to any other vertex information never lost or generated. So the flow that S sends outside, small s sends outside, exactly equal to the same amount of flow that leaves into T. Because this is just a cut, right? This will be just a cut where I'll use S as all the vertices and T will just be small t, both capital S, capital T. Okay, and let's hand wave or give the taste of the proof. We measure the flow at S itself. We measure the flow at S itself, and I'm looking at the flow that leaves S. Let's say 1, 1, 1 is a flow that leaves S. So I'll start at a case where I'll compute the flow from small s into all the vertices minus s. And this gives me some value. So right now my cut consists only on s from one side. This is capital S, and consists of t, which is any other vertex. That's where I defined the value of the flow. And now I'm looking at some vertex A, some vertex A that we see, like here, exactly like in the slide. Here is A over here, and let's assume that into A there is a flow of 1 that coming from S. Again, there is a flow of 1 that coming from S to A, and there is a flow of 1 that goes into A from some vertex B. So again, at the moment both A and B belongs to capital T, the right side of the cut, and small s is the only vertex that is on the left side. Now let's think about it. Out of A, there is a flow of 1 and 1 that comes into A, which means that by flow conservation, there is a flow of 1 and 1 that must leave A, right? The flow conservation says whatever comes into A must be equal to whatever goes out of A, which will implies right now that if I am changing my cut and I'm adding A into the flow, I'm adding A into S. So right now on the left side, I will have S and A, and on the right side I will have V minus S and A. Look what happened when I'm adding A into S. I don't need to count the one that goes in, but the one that goes in, let's follow it. The one that goes in was going out, is now the one that goes into A from small s is now counted as the one that leaves A from capital T. Now, there is another flow of 1 that leaves A as well, but that's because there is a flow of 1 that's going from S going into A from B. So this cancels this, and this cancels this. So I did not change the total value of the flow. So by adding A into S, moving A from capital T into capital S, I did not change the value of the flow. And that's almost the full proof. You can easily add, you don't need to, that's not the interesting lemma out there, but it's definitely catches what I just showed as an example, catches everything in the proof itself. So let's move on from this flow. However, you should remember, no matter which cut you're looking at, the total flow across this cut will be the same, meaning that no matter which flow we are looking for, we want to maximize this value. Next, let's us define the capacity of the cut. The capacity of the cut is just the sum of capacities of all the edges for which the edge is going from one vertex of S into one vertex of capital T. Look at all the edges that goes from some vertex of capital S into some vertex of capital T. Notice I don't decrease anything from it. When I define the flow, I also had negative terms. Now when I'm defining the capacity of the cut, I'm only considering edges that goes from capital S into capital T. And sum up these capacities. In 0-1 network, it will be in 0-1 network, it will be just this number of edges that you're counting because the capacity of every edge is 1. Arbitrary network, it can be, of course, anything. You still define the capacity of the cut as the sum of the capacities of all these edges. In our example, here is one such edge. This edge not counted because it's not from capital S to capital T. Both these vertices are in capital T. This edge not counted because it's going from capital T into capital S, and we don't care about it. We only count edges that go from capital S into a vertex of capital T. How am I doing in terms of lagging delay? My CPU doesn't seem overly excited, but it looks that I'm okay. People from the ones still alive? Any trouble? Okay, thanks. Okay, let's increase can I increase these letters a bit? Okay, here is the main lemma. It's a bit hard to see these letters. I'll write it. I know what I'll do. Better? Readable? Okay. I mean, you're alive. Is this readable now? Oh, okay. Yeah, the whiteboard doesn't. That's the only thing that is relevant. Just this summation. And there is a lot of small letters. Let's see what's written here. So I'm looking at the flow, which is counted as a flow. That's what the similar. I didn't tell you what I want to prove. Look at the value of the flow at every moment. As I said, there are okay. Since the whiteboard hides it, let's write it back. So I want to say that for any cut, capital S and capital T, the value of the flow is always small or equal than the capacity of this cut, the capacity from S to T. Remember, the capacity might change depending on which cut you are using. The flow is, you're looking at the network. What we just proved is that no matter which of the cuts I'll use, the flow across the cut is the same. The capacity depending on which cut I'm using. We want to say first that the flow never exceeds the capacity. And why is this? Let's look at the value of the flow, which we just proved that is a sigma over all vertices u V such that U belongs to S and V belongs to T of FUV. This is the value of the flow minus, now to compute the value of the flow, I need to now decrease some number. But there is another sigma comes here that adds flow from right to left. But that means that this is small or equal, then sigma of the flow from U to V. U is in S, U on the left side. V is in T, T on the right side. U in S, V in T, FUV. I'm just counting the flows that going from left to right, and I ignored this part completely. What do I do? Because I don't subtract anything, I just make it larger. Now, my next step is to say, I'm looking at exactly this sum, looking at exactly this summation, but instead of, I'll still sum from U in capital S and V in capital T, but instead of writing FUV, I'll write CUV, the capacity of the edge. That is, see what I'm doing? I'm looking at one of the edges. I'm looking at one of the edges, UV, and I can count it once as a flow. And here I'm looking at the capacity. What did we say? The flow is legit, meaning that for every U and V, this number is 1 in 0, 1. In any network, there is some positive number. To make it a legit flow, the flow across the edge UV cannot exceed the capacity. So this is small or equal. And that's essentially the whole lemma, because what you are summing up in the right side, what you're summing up right here, is just the capacity across the cut. What you are summing at the beginning of the sigma is a flow across the cut. What did we get? That's the, now let's move it back to normal size. What did we get? That no matter which cut you'll pick, look at the capacity across the cut, the sum of capacities of all the edges that crosses the river. No matter where the river passes, look at the capacity of all the bridges that crosses this river. This value, the sum of these capacities, is larger or equal than the total traffic that you can push over these bridges. No matter which set of bridges you can pick. Okay, and now we are getting into the highlight. Here is a max flow mean cut theorem. Look at the network at any particular moment. And there could be a few conditions that might satisfy or not satisfied. And the theorem tries to say if one of them is satisfied, then they are all satisfied. If one is true, then 2 is true, then 3 is true. And if 1 is false, then 2 is false, then 3 is false. And what are these conditions? The first condition asks, is the flow, is the value of the flow equals to the capacity of a cut for some cut? Remember, we always said that the flow is smaller or equal than the capacity of the cut of any cut. Now I'm saying possibly you find one special cut. There is one very critical cut, the most saddle cut in the whole network. And right now, the total value of the flow, you generated a flow which actually not only smaller than the capacity of the cut, but actually match the capacity of the cut. It's exactly the same value. Maybe it's true, maybe it's false. Maybe for every cut that you'll generate, the capacity of the cut is larger than the flow, strictly larger. And then this claim is false. But let's say that there is at least one cut whose capacity is exactly the value of the flow at the moment. Then if this is true, then obviously the flow that you found is a maximum flow. You cannot increase the value of the flow any further. You just reach the maximum traffic that the network allows you, which will happen if and only if Ford-Fulkerson will find no augmenting path. That is, if this is true, then Ford-Fulkerson cannot find any more paths in the network, which at this point it exits. And at this point, Ford-Fulkerson says, hey, that's a maximum, I cannot find anymore. So what this theorem says is that if you cannot find any more augmenting path, then it's because you just match one of the cuts, a critical cut, a mean cut actually, and at this moment you cannot increase the flow any further. The reason that you cannot increase the flow any further is not because Ford-Fulkerson is only mediocre and a better algorithm will do a better job, but because this is a global optimum and you cannot find, no matter, and you cannot integer, non-integer, no matter what you'll try, this is a maximum cut. And why, the reason that this theorem is so important, don't take my word, check the literature, the reason that this theorem is so important is you can think about Texas and electricity breaks. You can think about other networks, various examples. It's not only telling you what the maximum flow that you can send through the network. It also tells you what are the pieces of the network, what are the edges that are really bottleneck for increasing the flow. Where should you change pieces of the network if you want to increase the flow, or if you want to protect the network against various conditions and you have budget to protect only a few pieces of the networks? What are the most important pieces? What are the pieces that I'm absolutely sure that if you'll delete one of the critical pieces, then you'll have to decrease the traffic of the network, comparing to other pieces of the network where you can just redirect the traffic. Once again, trying to make this sentence a bit more in order, some pieces of the network really needs protection because if you'll hurt them, the whole network will suffer. And other pieces of the network are kind of robust, and if you'll hurt them, then you'll still send the same value of the traffic. Maybe you'll have to just reroute the traffic in a better way. And this theorem tells you exactly what are the most fragile pieces of the network. So let's see the first two claims. They are very easy. The third one we'll do at the beginning of next class together with a global review. And of course, we'll have a review before the final, as usual. Let's see why if 1 is true, then 2 is true. Why if I find any cut in the network which is saturated, namely the flow equals to the capacity of this cut, then it is a maximum flow. And that's obvious because we saw that no matter which cut you'll find, the capacity of the cut always larger or equal than the value of the flow. So if there is a cut that I found, one particular cut, critical one, which is now completely saturated, if I'll try to send more flow, then I'll violate the capacity of this cut. One of the pipe of this cut will be damaged. Okay, so if there is a cut which is fully saturated, then this is a maximum flow. But there is exponentially many cuts, so I don't suggest check all the cuts immediately. I suggest first find the maximum flow, and from the maximum flow, you can now generate what is a critical or the critical or a critical path, a critical cut. Now, let's assume that we find the maximum flow. I want to say that for Farrell-Kherson cannot admit any augmenting path. Why? Because the moment that I find an augmenting path, I can increase the flow across this path. But I just said, we want to say that if 2 is true, f is a maximum flow, by definition, I cannot increase the flow in any way. So in particular, I cannot find any augmenting path in the network. An augmenting path, even by the way it rings, is a path that you can add, you can push more flow through it, but I just said that it's maximum flow. So you reach the maximum. What we'll do at the beginning of next class is to show that if you cannot find any more path, then here is actually an algorithm that shows you what is a critical cut. What are the bridges that you must protect most in a most secure way. Okay. Any questions of everything so far?
I had a question about when we're going to receive grades for the last homework.
I think that
Have you received that yet?
for question homework 7,